Hello, I am Pratham Budev and I am partner with Dhanraj C. Parmar. Today we are excited to present our project lung disease detection as a part of our deep learning course. In this project, we explore the realm of deep learning to address a critical healthcare challenge, the early detection of lung disease, as we take you through our code implementation. And you will witnesses how advanced neural networks, particularly the ResNet 50 model, can play a vital role in medical diagnostics. So let's dive into the details of our project. First of all, this course involves creating a deep learning pre-trained ResNet 50 architecture. And now I am going to show data set of our project. Here, a bar plot uh, visualize the distribution of classes in the data set, and here you can see the test data, glimpse of the data. And uh, here we did data augmentation and splitting through image data generator. So image data generator is used for the data augmentation and enhancing the diversity of the training set, and data set was split into the training and testing sets to evaluate the model performance.
So let's understand the how we train the model and we take the outputs of the model. So first of all, this portion of code can be shown that we have three categories. Basically, the training data, validation data, and testing data is generalized for every deep learning or uh, deep learning models and machine learning models. So first of all, I can say that we have take a batch size as 32 because we are not progressing all the images at a time. We take the batches of 32 images in one batch and then we train the model. So basically, the first train gen variable has a training data gen model, and in which we had we put our data frame as a training images, which we specified for the purpose of training. Then we uh, take x column and y column variables for file path and labels, and then we take the targeted size of our image, like in 100 pixel in height and 100 pixel in width. Then after, the class mode will be the categorical class, because we are not having any single class to detect. We are four different classes to be detected, and batch size will be taken as 32. The training portion, we shuffle the image, so the basically training will be more effective. And we took the subset part of the first data, the training. For the valid gen, the things would be the same, but the subset will be changed to the validation portion, and shuffling will be false of for the training. Sorry, for the validation part. For testing, we remove the subset part and the shuffle part, because during the testing we firstly we not take always as a training sorry testing that to be shuffled, because we direct need to be tested, so the result can be observed. uh, okay, and the next. So here we take the ResNet 50 model, which is containing the input and output, also the pooling values and the weights. So first of all, during the input neurons, we take three batches of 100 by 100 neurons for the input because the image is RGB. Then there is a weights parameter. The weight parameter defines what kind of weights values is suitable for the model. And then after the pooling means we took the average pooling of for the model, and we said that a pre-trained model is trainable to false because we don't want to ready-made model to be trained. We need that model to be trained in separate. Then we took the inputs uh, as a inputs is a variable to accept the inputs of the image pixels. So in our pre-trained model, inputs will be there. We take the same inputs for the inputs variable, and then there is a x means the dense layer. So basically, we took the two dense layers, each containing the 128 neurons with the activation function of ReLU, and the outputs will be also the dense layers, but the length of whatever the length of the trained data chain with the activation function of softmax, because we are saying that this output will be belongs to any four classes. So for the softmax function will be useful. And then after we took the inputs as inputs and outputs as outputs for the model. Uh, then below that, a model.compile that will be started to train the model with the ADAM optimizer and the cross entropy loss. And very basically, we took the matrices to be uh, observed as a accuracy matrix of the model. And then we started our training process. We started a model to be fit with the training data, and the validation data will be validation gen data, and the overall epochs will be 20. So in 20 epochs, we train our model. Okay, scroll it. So these are the 20 epochs will be completed, and after that, we save our model to be test later. So whatever the model will be trained at the time, that model can be used for the testing purpose later. Scroll it, scroll it. So here after the training and the saving of the model, we are displaying the two graphs with the accuracy and the loss. So in both of the graphs, you can see the first graph is for accuracy and second graph will be the loss. So over a time, you can observe that validation accuracy is remaining constant or some of the different values, but the overall accuracy is increasing continuously over the time. And below the same for the loss graph. So the validation loss is nearly increasing over the time, but the overall loss is decreasing continuously over the time. So we can say that our model has a better accuracy and better loss. Then after we evaluate that model for the accuracy and testing purpose. So for the test loss of this model will be the 38% total lost in testing, and accuracy is the 91.87% test accuracy for this model we took out. And below we predict the labels. So for testing data, we predict the labels, and the training data we predict we are setting the labels. So overall output of this cell is like 48 images are there to be predict with the testing data. And each testing data you can see over the period of time. The first image is just a normal output. It shows the normal. Second also the normal, and third, fourth, and suddenly the fifth one is said to be cardiomegaly or falls into cardiomegaly category, and seventh or eighth one is falling in COVID category. So that's in the now in this cell we test no sorry yes we test the precision recall and F1 score of the four categories: cardiomegaly, COVID, normal, and pneumonia. So overall, the COVID has more support and more precision recall and F1 score values. Means the whatever the COVID image data is there, it's for sure that the by scanning that X-rays, it concludes that this person has a COVID or this person has come a cardiomegaly or pneumonia. So below you can see that accuracy, macro average, and the weighted average of the precision recall and F1 score. And below that we plotted our graphs that which visually that which image is containing the true label and containing the predicted label by the model. So you can see there is a true value for first image, there is a true value for pneumonia and predicted is normal. So model predicted this image is a normal X-ray, but it's X-ray for the pneumonia. And you can see the second one, it's predicted the normal, and it's actually true that the X-ray is a normal person. Now these are the some of our outputs as nearly 10 outputs is there. Scroll it, scroll it. So here you can see all of them. And at last we took the image testing image for a testing purpose for 3.png, and we resize it to 100 by 100, and we uh, take that image and tell model to that predict this X-ray image for the one of the category, and the model predicts here you can see the 0, 59, and 39. So it means that the image is more score in the third category, which might be category for the so Pratham just no, just open the data set category so we can see the what is the third category. So yes, the third category is for the normal ones, I guess. Yes, it is for the normal ones. That the 3.3.png image is the normal X-ray image of a person. Then let us jump over the comparison of the models in test.apnviewer file. So first of all, we import all our usable dependencies for this file and for this purpose. Then we can scroll it down. Then for this cell, we first of all load the data set, and we took the all file paths from the data set by continuously jumping and changing the directories. Then we took that all names or four categories in one data variable, and we concat them all together. And then we are training in then we are splitting our data set into the training and testing purpose. So that is whatever So if we say that we have four categories and 5,000 images, then out of that 5,000 images, test size will be 20%, and it will took the random images of 42. Then we use the label encoder for the training and testing label. So actually we can know that the predicted image is correctly predicted, or the actual image is different one. Okay, scroll it. Then we write code for the data augmentation for the training data purpose. So what we took that image data generator is a by default library that we have import for the data augmentation purpose. So while during our training, we are changing the images properties like rescaling images, rotation of the images, width and height of the images, horizontal flip or not, and fill mode. So you can see that we have set all these parameters to for a training purpose. For the testing purpose, we have only used for rescaling attribute of image. So we are only rescaling the image, not any other properties of image. And for the training, we took the again the training data and x column and y column for the file path and labels. Also, we took the target size image will be the 100 by 100 pixels in the batch of 32 with the class mode of categorical. For the same purpose, test gen data is prepared, and same attributes like batch size, targeted size, and class mode. Okay, scroll it. Then we encode the labels from the label encoder, and you can see that there are outputs of the cell, like there are 6210 validated images and files name belonging to class 6, and also the 1553 images and from the class 6. Now scroll. Then we took our first model, CNN, to be run. In our CNN model, we took the sequential approach. Like the first layer will be convolution layer, 2D convolution layer with the 64 neurons with the activation function of ReLU, and input range will be the 100 by 100 pixels, means there are 200 pixels at the input side. And then we took the max pooling layer, and again the convolution layer and max pooling layer. So there are two convolution layers and two max pooling layers. Then after we took the flatten layer, so the model can easily process over the data. And then after at last we took the dense layer with the size of label encoded classes, and that dense layer having the activation function of softmax. So we can predict that out of four categories, which categories that image is belonging. Then after we compile the CNN model with the ADA optimization with the learning rate of 0.001 and the loss accuracy, again the cross entropy, and the matrix is accuracy to be observed. Then we started the training of CNN model with the training generated data, and epochs will be 10. The validation data is test gen, and we took the early stopping whenever the model is completely suitable for the validation and testing it's to be true. So like if in the fifth epoch your accuracy is 99%, then the model will stop be training, and the final model is considered as a best trained model. So here that CNN model is completed with the 10 epochs, and after that we took the ResNet model. So for the input of ResNet model, again will be the 100 by 100 pixels of input, and weights value is set as the image net weights, and pooling layer is average pooling. Then for each layer of ResNet model, we say that layer is not trainable, and we the first layer of ResNet model is set as a trainable. And again, the process is a sequential process. First of all, the ResNet model is there, and then at last there is a dense layer with the activation function of softmax. Then we set a compilation parameters of ResNet models like Adam optimizer with the learning rate of 0.001, and the matrices to be observed its accuracy. Then the ResNet model.fit will be started its training with the trained data gen, and epochs will be 10 with the validation data is set to be test gen data. And here also we use the early stopping method. And at last we took the VGG16 as our third model with the same attributes like a ResNet model is 100 banded input images, weights will be matchnet and pooling layer will be average. And also the layers of the VGG16 model should not be trainable instead of first one. And for the sequential process of VGG model, and at last there is a dense layer with the activation function of softmax. And the compilation parameters are Adam optimization, the 0.001 learning rate, and the cross entropy for the loss, and matrices is accuracy to be observed. Okay, so at last there is a VGG model.fit. It started its training, and epochs will be 10, and early stopping will be there. And here in this cell, we took the comparison of three models. So like which model having the highest accuracy. So you can see that the CNN test accuracy is 79%. It's higher than the ResNet model and which is 16 model. Okay, scroll it. And last cell we have just printed over there is that the which model is best one with its accuracy. So obviously, the CNN model is the best one with the accuracy of 79.27%. So this is the comparison of three models and how we train it. So over to you, Pratham.
Hello everyone. Uh, Now we will walk through the project run.py file, discussing how it loads a pre-trained ResNet 50 model and predicts lung disease conditions, lung conditions, and based on an input image and visualize the present the results. Now here we are loading the ResNet model uh, by loading a pre-trained ResNet 50 model using TensorFlow's Keras library. The model is saved in the for underscore model underscore ResNet 50.h file. So here we if there is any another pre-trained model, so here we have to change the path. But now we already now here this is the for to take a input image from the user through CMD. It is the type of the image like .jpg, jpeg, png, and now we are going to categorize the list. We defined a list of categories representing different lung conditions like cardiomegaly, COVID, normal, pneumonia, The script uses a Tinker and GUI toolkit to prompt the user to select an image file, and the selected file path is stored in the IMG path, the IMG path variable. And if there is no image selected, then it will print no image selected. And now, once an image is selected, we ready and pre-process it using OpenCV library. The image is resized to 100 cross 100 pixels, and the pre-processing is performed to match the model requirements using the process input, process underscore input function from ResNet 50. And uh, if any type of disease will be predicted, so text color or title will be changed to red, or else if it is normal, if predicts normal, then it converts into the green color, text color will be converted into green. And here we are sorting the averages, the predict average of the disease, lung disease. It is sorting in a descending order form. Now we will perform a practical. First, we select a normal image. Here you can see if predicted is normal, then it turns into the green color. And here it will sort in the descending order. Like normal has 99.14%, pneumonia has 0.86%, and COVID and cardiomegaly is 0%. Now you will take some disease image. We will take some images from the Google. I already download some images for testing. First, we will see COVID image. See, predicted is COVID, so it turns into the red, and COVID has 100%, and other has 0%. We take a pneumonia image from the Google. See, uh, predicted pneumonia, but pneumonia has 65%, and normal has 18%, and cardiomegaly has 14%, and COVID has 0.97%. So it sorts in the descending order. Uh, Thank you.